Okay, so in this video, we're going to continue on with chapter 4. So we talked about the first few bullet points in our last couple of videos. Now we're going to get down into some of the nitty-gritty down here. So first and foremost, we've been talking about the periodic table. Now we know how to identify elements on the periodic table. However, why is it the periodic table? Like, why is this periodic table the one we use? Well, there was a scientist called Mendeleev. He looked at the elements in order of relative mass and saw trends and behaviors in the properties of the elements. So as he arranged them, he didn't know he was arranging them by protons because he passed away before we discovered protons. But he arranged them in this manner, and this helped him see patterns and repeating trends throughout the periodic table, and we use those patterns and trends and get information from the periodic table based upon the location of those elements. So that's why the periodic table is important and how we kind of got to it. It's all these repeating patterns. It's also really interesting too because as Mendeleev put out his version of the periodic table, it wasn't as full as the one we have today. So the one we have today is much more full. So basically, because he saw these trends, he was able to predict that there would be more periodic or more tables on the more elements on the periodic table, and that they would have certain properties that would fall in line based upon where they were expected to be on the periodic table. Lots and lots of scientists after that, it was basically like open season duck hunt. All the scientists, all the chemists were going immediately after trying to have an element on the periodic table to discover it, because now they had these properties and clues and they knew that they must exist. So they were able to use those clues to start to fill in a lot of the stuff, a lot of the rest of the stuff down at the bottom of the periodic table. We were able to start kind of isolating and actually confirming that those elements existed for the first time. It's easier once you know that something should exist to discover it than to pull it from thin air, right? So there are many different types of elements, and we'll talk about a few different ways we classify elements on the periodic table in this video. However, one way we might classify them is like what I'm going to call types of elements. So when we look at the periodic table, we'll generally see 3 different types of elements. You can see here that they're denoted in tan and purple and green. So the first group of elements we'll talk about, very common, we come across them quite often, they're called metals. So metals are going to be on the left-hand side of the periodic table. They're almost all of the periodic table. They're everything over here in tan. We're grouping them together based upon general properties and traits they have. So metals are good conductors of heat and electricity. They're malleable, so we can shape them into things. We can pound them, and they pound flat. They don't just break apart like other things do. They're ductile, so they can be pulled into long, thin wires, atom by atom if we had to, which we can't do with everything. They also tend to be quite shiny. Humans like shiny metals, so we tend to make rings and things out of gold because we can shape it into that circle and it's quite shiny and we like it. And the thing that's really interesting about metals in terms of what we're going to talk about in chemistry class is that metals tend to lose electrons when undergoing chemical changes. So we can kind of count on a metal to lose electrons as it's going along. Some examples of some metals that you might be familiar with would be like iron, Fe, that's a metal. Magnesium is a metal. We used that in lab this week if you've been in lab. And then sodium, that's in table salt. It's in a lot of things we come across in our daily life, but those are all going to be considered metals. We also have the non-metals in contrast, so metals, non-metals. So our non-metals are going to be up here in the upper right-hand corner of the periodic table, and hydrogen. So hydrogen's green, it's not a metal, we consider it to be a non-metal. It fits very well and very nicely here on the periodic table, the way we set it up. However, in a lot of these groups, we'll talk about hydrogen being an exception. We kind of consider, when we're talking about the first column, if I'm ever bringing that up, I probably mean lithium on down, not really including hydrogen. There are certain reasons we'll talk about later why hydrogen fits well here, but you just got to remember hydrogen's the one non-metal that's on the wrong side of the periodic table. So the rest of our non-metals are going to be over here. Hydrogen's on this side. Non-metals tend to be poor conductors of heat and electricity. However, they have more varied properties and levels of reactivity overall. So they're a bit harder to nail down, but basically you've got the metals and then you've got the non-metals that aren't metals. These are going to gain electrons when we're talking about chemical changes. So they tend to gain electrons when we undergo chemical changes. And they're going to have more varied properties overall. We might think about oxygen, nitrogen, chlorine, and argon are all nonmetals, for example. The third grouping that we have are these couple of purple elements here. So these couple of purple elements that ride this jagged line in between the tan metals and the light green nonmetals are the metalloids. So the book often calls these semiconductors. However, I don't tend to call them semiconductors. I will tend to refer to them as metalloids, so that way you know what I mean. They're going to fall on that diagonal line between the metals and nonmetals. And the reason we have like metalloids as a separate group is because they have this intermediate electrical conductivity. What in the heck did I just say? Basically, we can control the conductivity and change the conductivity of different semiconductors. So this is what allows us to use them in our technology. We can kind of boost how well they pass electricity on, so we can make them superconductors. But semiconductors allow us to kind of basically pass that information on at a single time point where we can have those on-off 1 zeros, the binary code that runs the deep base of all our technology. So that's kind of what computer chips are doing, is they're taking, they're using semiconductors to either stop or allow current to flow to meet a 1 or a 0. So our technology runs on metalloids or semiconductors. So that's going to be all of these guys down here. So boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. So those are going to be the metalloids for our purposes. So basically, you got to know that the metals are on the left-hand side here. You got to know that the nonmetals are on the right-hand side, and the metalloids sit between them. If I ask you, is this element a metal, you should be able to tell me yes or no. If I ask you if a metal is, or if something is a nonmetal, you should be able to tell me yes or no, based upon the location on the periodic table, or a metalloid as well. That's kind of what we're looking for here. And again, that's because we can tell that they have specific properties, whether it's a metal, a nonmetal, or a metalloid. So that's one way we can talk about classifications on the periodic table. Another thing that we talk about quite often are main group versus transition elements. So main group elements versus transition elements. So when we're looking at our main group elements over here, that's going to be everything in yellow on the left and right hand side, and the transition elements are going to be listed in blue here in the center. So if I ever say main group, I basically mean the first 2 columns and then the last big chunk over here, the last 6. And if I ever say transition elements, we're usually talking about everything in the center of the periodic table, including those lanthanides and actinides that usually sit down at the bottom of the periodic table, but this one doesn't show for whatever reason. Another way you can remember it is main group elements are listed with A in their group number in that column name. They've got all A's, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. And the transition elements are listed with B's, so 3B, 4B, and so on and so forth. So I may also talk about main group versus transition elements as well. We often use the main group elements in this class. We've seen a lot of this stuff on the side. We saw some potassium in lab, some chloride, some magnesium, some zinc. So I guess zinc's a transition metal. It wasn't in my head. So zinc's going to be a transition element we saw in lab this week. We're going to see cobalt. So while most of our chemistry is ending up over here, carbons, oxygens, hydrogens, we may see some of these things in our complexes. I guess we saw copper too, So we saw 3 transition metals this week. Nice. So in lab we saw iron, or we saw cobalt, copper, and zinc. So We saw some transition metals, but again, the majority of everything we used is going to be main group elements. 9 times out of 10, we'll be talking about main group stuff. Or maybe just a couple of these transition metals on the top row. There's one other way that we generally talk about things on the periodic table. To me, families are a more kind of specific classification of metals, nonmetals, metalloids / main group transition. So we can also talk about families of elements. So these are going to have extremely similar properties based upon their groupings, basically. So we kind of looked at them and we said, these guys in these columns have such similar properties, it's important for us to talk about them. So we'll talk about 4 main families that we'll use in this class. So the first one is going to be alkali metals. So we could have alkali metals. These metals are very reactive, especially with water. I have a video here linking to a video of different reactions of alkali metals with water. They start with lithium and they work their way down to cesium, and then kind of have a, this is what it would look like if you had francium. We don't, francium isn't naturally occurring. We'd have to generally make it in a lab. So we don't have it for a fun blow things up science experiment. But if you want to watch some reactions where we're dropping these extremely reactive metals in water, you can check out the YouTube video there. They're super reactive. Actually, spoiler alert, a bathtub gets blown up. So fun video, check it out so you can see that that's why they're grouped together. They're all stinking reactive that way. And they fall in the same area on the periodic table. So we can say, okay, group 1A are the alkali metals, is what we named them. Group 2A here, before we move on, Group A or Group 1A, when I'm talking about Group 1A and I'm talking about specifically the alkali metals, that does not include hydrogen. So I'm talking lithium, sodium, potassium, rubidium, cesium, and francium. I'm not talking about hydrogen. Yes, it sits here on the periodic table, but it doesn't exhibit the same traits as these families, you know. It reacts different in water than these, so that's why we have like lithium through francium as our alkali metals rather than including hydrogen. Our second group is the alkaline earth metals, so it's kind of confusing because it's alkali metals and alkaline earth metals, so you got to remember that, but they're the second column. So they're going to be beryllium, magnesium, calcium, strontium, barium, and radium. So these are all of these guys here. They're reactive with water. They're pretty reactive with water, just not as reactive as the alkaline earth metals are. But they exhibit a lot of the same traits and properties, so we consider them to be a family as well. And then the other ones we're going to talk about moving from left to right, so that would be alkali metals are the first column, alkaline earth metals are the second. Halogens are group 7A, so those are the halogens. We come across them all the time. You know, we think about halogen lights. Things might be halogenated, something like that. They're very reactive nonmetals. So these guys are a lot of our main prime suspects when we're talking about nonmetals. We'll see a lot of carbon, nitrogen, oxygen too, but these really are our usual suspects. They're usually the ones getting down and dirty, doing most of the work. And then our last column here is column 8A. That's the noble gases. So the noble gases over here are kind of special because we've talked about how the first 3 groups are very reactive. The noble gases are quite the opposite. They are not reactive. They do not want to do anything. We call that inert. However, I'm cool with just the term not reactive. So sometimes you might see them called the inert gases. We usually call them the noble gases, kind of an antiquated term from back in the day. You know, they didn't interact with the general masses of the rest of the periodic table, so they were noble like the noble people. Call the rest of the periodic table a bunch of plebes. The noble gases didn't want to interact with them, so not reactive. They don't like to form what we'll call ions in a minute here. They don't like to do anything. They just like to exist as themselves, the noble gases do. So those are the 4 main families that we're going to talk about here. So if I'm talking about alkali metals, you better know which ones are which. And if I identify them, you should know what I'm talking about. If I just say, oh, the alkali metals, you'll think, oh, yep, this first column periodic table. So We also have two other groups that we talk a little bit here. We won't go into very much detail on these and we won't talk about them much. I actually didn't really talk about them much till I got to graduate school and I started doing research on these elements. These are the lanthanides and actinides. They are really, really heavy elements. So they sit down at the bottom of the periodic table and actually they kind of slide right in. If you check out here, we've got 57 lanthanum, but we have 72 hafnium. So the thing is you don't just jump from 57 to 72. 58 through 71 are just held below the periodic table. And same thing for the actinides with these. With rutherfordium and actinum being right next to each other. Obviously 89 and 104 aren't directly there, but 90 through 103 are located down here. So our lanthanides and our actinides are going to slide into the periodic table there. So we could almost imagine it like our periodic table is actually expanded out. So the thing is we could have a periodic table that's like as wide as my entire computer screen, that's as wide as every chemistry lab we work in by including those up in the periodic table. But we set them down below because they're a decent amount of elements. And it just helps us kind of keep everything a little bit more compact and condensed. So you'll see down below that these are the lanthanides and actinides, but they really exist like right here in the periodic table, and we could just scoot out those transition metals. So it kind of went down 2 steps, down 2 steps, all of the lanthanides and actinides back up to titanium and zirconium. So we'd have a big gap, and then we'd fill in the rest of our periodic table. So those are the families we expect to use in this class. So we've talked a little bit about where things are located on the periodic table. You should be able to identify if something's a metal, a nonmetal, or a metalloid. We should know if it's main group, transition, or know if it belongs in one of the 4 families listed here: alkali metals, alkaline earth metals, halogens, and noble gases. And then we'll be able to start to use those properties as we go along. So that's how we might group some elements on the periodic table.